Hello, I'm Minyoung Park from the Dongguk University, currently reviewing papers for the winter break. In this seminar, I'll be reviewing a paper that explores how the RAG model can be applied to extract engineering design knowledge, which I plan to use in my master's thesis. The contents are the same as the structure of the paper. This paper was published in Knowledge-Based Systems, Q1 journal. It focuses on extracting explicit facts, subject, head entity relationships, object, tail entity from patent data and applying these facts to an LLM using the RAG model. The first section is the introduction. The paper starts by emphasizing the importance of LLMs. While models like GPT and Llama have been widely used in areas such as chatbots and writing assistants, they are not well suited for knowledge-intensive tasks like engineering design. This research therefore proposes a method for extracting explicit fact relationships from patent documents. These relationships are represented in the triple formats: head entity relationship and tail entity. Similar to the subject action object, as you know, SAO, relationships we work with in the lab. To extract these relationships, two approaches are necessary. First, relationship identification step involves identifying entities in a sentence and fine-tuning the language model to predict token labels like those tags. And relation elicitation step involves fine-tuning the language model to extract actual relationships from sentence containing entity pairs using sequence-to-sequence or text-to-text approaches. Now, I'd like to explain the main objectives and contributions of the paper. The study aimed to extract explicit fact relationships from patent documents related to artifact technology and build an engineering design knowledge base. The goal was to identify explicit relationships between entity pairs, which are represented in the formats head entity, relationship, tail entity. The key contributions include proposing an engineering design specific approach distinct from traditional knowledge extraction algorithms, and providing a manual and dataset for identifying design facts in over 50,000 sentences. Additionally, the study contributed by releasing a total 375 84 datasets and training infrastructure as open source. Finally, as a real-world application, the paper demonstrates the RAG methodology based on domain knowledge from Venn system patents. Moving on the background section, knowledge extraction algorithms involve processing text. Named entity recognition is the task of identifying entities in sentences and classifying them, including predicting the relationships between classified entity pairs. These tasks are primarily trained on standard dataset like ACE10, WNUT, and onto nodes. NLP researchers have proposed various algorithms for entity and relation extraction. Traditional algorithms use syntactic dependencies to learn relationships between tokens or praise, while language model-based algorithms fine-tuning models like bots to classify entity categories and predict relationship classes. Engineering design knowledge involves extracting entities and relationships. Previous studies have used TF-IDF values to extract key phrases from patent documents and papers, and they built domain ontologies using relationships like type of or consist of. Some studies also use synthetic dependencies and birth-based similarity to construct networks of nouns and verbs. Engineering design knowledge text includes descriptions and relationship related to artifacts, conveying structure and behavior relationships between entities. While existing research aimed to simplify these relationships into finite sets of alternatives, this study proposes a methods for identifying explicit facts in sentences. Instead of focusing on a specific domain, this study aimed to develop a method for extracting knowledge from patent documents. Now let's talk about the dataset. The study sampled 4,205 patents from the USPTO, categorized hierarchically according to CPC classification system. The sample size was determined using Corcoran's formula to ensure a 99% confidence level and a 2% margin of error based on a total of 4.8 million patents. They crawled patent document section from Google Patents, selecting sentences under 100 words, resulting in a total of 51,232 sentences. Irrelevant sections such as background information and unnecessary special characters were removed. Engineering design experts identified entities and relationships within the sentences, mainly focusing on hierarchical and attributes relationships. A web-based tagging interface was used for fact identification, allowing explicit facts to be extracted. In terms of results, representative sentences and examples are provided on GitHub. During the relation extraction process, over 50,000 sentences were used to select entity pairs and relationships based on noun phrase, creating training examples. Each sentence's entity pair was labeled as head and tail, and language models were fine-tuned to predict or drive relationships. In the relation identification phase, training examples were created with tokens labeled as head, REL, tail, or OTH, which were fine-tuned with a token classification model. Entities were selected from noun phrase using species transformers, and transformer-based models like small, large robot base. Some BERT models were also used. In the relation elicitation step, training examples were generated using marked sentences with relations, and these examples were fine-tuned for sequence-to-sequence tasks. The model used were BERT and T5 encoders. As alternative approaches, link prediction methods were used to classify entities and relations as ENT, REL, and TH, and neural networks were employed to predict relationships. The performance results show that GNNs performed poorly and MLP caused issues with positions. The link prediction method was more complex for training and application. The relationship identification approach demonstrated better performance and scalability. For the application, the goal of this paper is to explicitly extract engineering design facts and propose methods for using large language models to generate domain-specific responses. The GPT-4 Turbo usage scenarios for event systems are described. Scenario 1 involves directly using prompts, while Scenario 2 and 3 refer to using the original text and explicit facts. With this approach, we built a knowledge base containing over 2.9 million facts extracted from 4,870 fan system patents in the F04D subclass. This knowledge base is accessible on Hugging Face. Example scenarios are as follows. Scenario 1 directly requests generalized knowledge of fan systems from a simple LLM, while Scenario 2 provides the titles and abstracts of 10 randomly selected patents. In this scenario, the LLM summarizes each abstract into short sentences but does not provide a consistent domain description. Scenario 3 offers 177 recurring facts as references, where the LLM generates a consistent description of band systems. In the design process, there is a need to explore or convey generalized knowledge about the product domain. 3 scenarios were used to apply LLMs in the fan system domain. Scenario 1 requested a general knowledge from the LLM, obtaining Wikipedia-style responses that were not useful in the design context. Scenario 2 provided 10 patents, titles, and abstracts, but the domain's consistency was lacking. In Scenario 3, by referencing 177 recurring facts, the LLM generated a consistent explanation of fan system, allowing the integration of important attributes to domain knowledge. From 2 million facts, frequent entities and relations were selected to derive 177 facts, which facilitated to reg function. The following is a portion of the 177 recurring facts that represent generalizable design knowledge of fan systems. An interactive graph can be viewed externally. In a design environment, domain-specific knowledge for subsystems or specific problems is required. When the airflow noise issue was requested from the LLM, Scenario 1 provides only speculative causes and solutions without sufficient detail. Scenario 2 summarized 559 related sentences, but the summarized content tended to infer other phenomena as the cause of noise reduction. In Scenario 3, 131 selected facts were referenced, and the LLM provided more specific solution, which could be traced back to patents. This demonstrated that when domain knowledge exists as explicit facts, it enables the reg model and LLM responses can be traced back to actual patents, ensuring the reliability of AI system in engineering design application. The following is a portion of 141 facts constituting specific knowledge of the airflow noise issue in fan systems. The entire knowledge graph with interaction can be viewed externally. For the conclusion and summary, this research introduced an explicit fact extraction method that extracts facts in the form of head entity, relationship, tail entity from patent documents, enabling reg support for LLMs. A dataset was created from 34,227 documents, showing that both generalized and contextualized design knowledge can be extracted. This work enhances the potential of LLMs in engineering design applications by providing a design knowledge base for generating technical and cohesive responses. The paper's limitations include computational cost, which may rise as the document set grows, and the lack of quantitative evaluation of the LRM's contribution to design, understanding, and creativity. Future research will explore how REC can aid in knowledge intensive design tasks and compare it with existing search methods like text embedding and PM225. Thank you for listening.